Okay. All is good. And perfect. So and it's time. So let's get started. So yeah, good afternoon. Welcome everyone to another lecture in computer architecture. Today we're gonna first continue what we have left off in memory latency lectures. We're gonna see a lot more techniques that in the line of optimizing the systems to not design for the worst case scenario essentially. And later on, we're gonna start lecture 9B, which is memory controllers. So we have a kind of ambitious plan for today. Let's see. Okay, so any questions? Okay, so remember that our basically goal through the last week lectures was to provide fundamentally low latency computing architectures. And we discussed about this graph, which for some reason it's not showing well. I don't. It was correct actually on my, but anyway, we're gonna see. Essentially, yeah, in this plot, which you remember, the memory latency has not been improved much. And we discussed about the different reasons that we have such a profile. The reason one, which we actually spent a lot of time on it last week, was to basically the design of DRAM microarchitecture, which is optimized for capacity and cost. And that's the main goal that people have had in the DRAM architecture. And basically, we try to challenge that goal and show some techniques which you can apply to improve latency as well. So in the end, there is no magic. When you want to improve latency, you're gonna probably lose some capacity, some density, but I mean that's a trade-off that we should consider. So it's one of the angles that you can consider when you're designing memory architecture. And then we start describing going over the second reason, which is that the memory architecture people have designed it for the worst case. There are a lot of parameters in our DRAM when we want to access it, and all of them actually they are optimized, or let's say they are tuned for the worst case scenarios. And why is that? Because they wanted to have a good yield such that all DRAM modules or DRAM chips, they work within that timings, essentially. We started with the work adaptive DRAM, AL DRAM, which actually mostly focus on DRAM temperature. And we show that in most of the timings in DRAM, actually they are optimized or they are tuned for the temperature of 85 degrees. But in reality, in personal computers, actually, for example, usually DRAM temperature is around 50 degrees Celsius or so. Also in servers, DRAM temperature is usually around 30 degrees Celsius. That may not be true for high bandwidth memory. So people should also do another, maybe, revisit such ideas for HBM, because when you have 3D stacking, that can generate more heat. Yes. Yeah, so yeah, for that, maybe you can check our last week lecture because we actually showed the profile, but today I'm just going over the overview of those works. I'm not sure if we don't have this slide for that today, but yeah, I also don't remember on top of my head, so maybe you can check the slides from last week. Yeah, essentially, but if we consider current temperature and also current DRAM module, because different modules are also different. Some modules are faster, some modules are slower. You can actually optimize DRAM timing for the common case. And we discussed about this work, adaptive latency DRAM, and which provide performance for us. Okay, and if you want to learn more about this work, you can check this paper. And then we asked this question that, is there also latency variation within a chip? And so the answer is yes, as you can imagine. And basically, that's the place we left off. And now we want to continue. Questions? Okay. So Yeah, so let's jump into latency parameters for all parts of a DRAM chip. In this plot, we are showing TRCD, which is you're gonna also learn about these timings parameters when we start memory controllers lecture. But essentially, TRCD is one of the important latency parameters that we need to obey when we work with our DRAM chip. So the standard on the date that we were doing this experiment was around 13 nanosecond. So this is the standard TRCD that we have to obey. But so in this analysis, we tested 240 chips, and we have done 7,500 runs of these experiments. So basically, because sometimes you do experiment, you don't see error, but when you repeat the experiment, you might get some errors. So we have done this experiment for 7,500 times, just to make some enough confidence for our experiment. And essentially, we reduced the TRCD from 13 nanosecond to 2.5 nanosecond. And on the y-axis, we are reporting bit error rate. So we observed that until this point, which is something around, let's say, 8 nanosecond or so, we haven't observed any activation errors. So basically, you can reduce latency, let's say, with high confidence and without worrying about getting errors by that amount. But then starting from 7.5 nanosecond, we started to observe errors. And you can see that we actually have a distribution here, that there are some chips that basically they don't see a lot of errors, or let's say there are a lot of different parts of the chip, because it's actually getting information across the whole DRAM chip. It's not only, the granularity is not per chip. So essentially, there are some parts of the DRAM chip that they can actually work nicely with 7.5 nanosecond, but some other parts, they have a slightly higher bit error rate. And the maximum, we can see that the bit error rate is around 10 to the power minus 1. So if you work with 7.5 nanosecond, there are actually many of chips that you can actually work properly, assuming that you can, because you also have ECC that you can also correct errors. But there are some parts of the DRAM chip that you cannot operate on that, and for those you need to operate on basically longer TRCD. And if we reduce TRCD more, like to 5 nanosecond or even to 2.5, you can see that most of the chips actually they all fail. Once you have a bit error rate of 1, basically you're gone, right? You have error 1 bit, basically error per 1 bit. So you cannot succeed. So that's a profile that we have, which is we have a nice variation in activation errors. And yeah, so we can actually benefit from such results. And also here you can, by checking only one DIM, you can see that. And when you read the column address, so basically you open, so on the y-axis you are observing the different rows, like rows 16,000 to row 0. So this is the y-axis, like different rows. And on the x-axis, we are showing the cache line, which is the column, essentially, the column address. And so the area of this plot is actually showing the bit error rate. And it's actually the distribution using this color. So here you can see that most of this plot is actually white, meaning that if you operate at 7.5 nanosecond, most of the chip, the DIM does not actually experience any error. So it's completely white. But there are some parts that you can see that you have some errors. And the interesting part is that we have some essentially special locality in that. So there are some columns essentially that for those you need to, if you operate on TRCD 7.5 nanosecond, you're gonna experience errors. So if you know that information, for those columns that you are not experiencing any error, you can actually use this error rate, this RCD latency with high confidence. But for those columns, you need to probably use a longer TRCD. Make sense? Okay. So that's observation that DRAM timing errors, slow DRAM cells are concentrated in certain DRAM regions. And so with that, we can propose flexible latency or fly DRAM, which is a software transparent design that reduces latency. So the key idea is that to divide memory into regions of different latencies. And also from the memory controller, we need to make it more complicated, essentially. So use lower latency for regions without slow cells and higher latency for other regions, essentially. So yeah, here is the configuration for fly DRAM. For example, this is the baseline DDR3 that you need to operate on the 13 nanosecond TRCD for essentially for all cells. And here are different DIMMs. So there's a profile of 3 real DIMMs that we are showing here. In DIMM D1, for example, this portion you can operate on 7.5 nanosecond, and the rest you need to operate on 10 nanosecond. So DIMM2, actually you are more lucky. So you can actually, most of the distribution fraction you can operate on 7.5 nanosecond, and a little bit on 10 nanosecond. And DIMM3, you are even more lucky. And also similarly for other timing parameters, which we have for pre-charge latency, for example. Okay. So ideally, we want to operate on 100%, but we cannot do that because we want to avoid errors. Yes. Well, the goal for this work is that, yes, to have it independent, because exactly, because it's a software transfer. But how can be related? Maybe that's my question. Can you provide some, context? Mm-hmm.
Maybe some workloads have better spatial locality processing.
Yeah. So yeah, essentially, if you have that kind of information, you can potentially map, some application data on those columns that you have less errors. Or even also later, I'm going to discuss some works in the line that if you know that your applications is, for example, error tolerant, you can map the part that they are error tolerant on a slow columns, which when you operate on that slow columns with low TRCD, you're going to observe some errors, but hopefully that error is not very important because that part of the application is error tolerant. So if you can, of course, if you can transfer that information to a nice channel to the memory controller, which makes your design more data aware. Remember that we were discussing about data aware architectures. That can actually improve performance, of course. Yeah. Good question. Any other question? Good. Okay, so, and here are the results which we can get. So the baseline DDR3, this is the performance which, this is exactly 1. So everything is normalized to the baseline. And so other different, when we apply fly DRAM, but on different DIMMs, depending on the profile. So remember that DIMM1, we couldn't actually operate on 7.5 nanosecond most of the time. So just to remember you, it was mostly actually you need to operate on 10 nanoseconds. So that's why the improvement on fly DRAM when you use on it on DIMM1 is only 13%, but on DIMM2 you get a lot more performance, and also on DIMM3 you get even more. And that's the upper bound. Essentially, if you operate, ideally, if you can operate on everything at 7.5 nanosecond, that's the performance gain that you can achieve in our experiment. But of course, this technique is not so easy actually to implement. So I'm going to also show you some later works that with those work actually we make it more possible, to implement. Similarly, remember about retention retention time errors. And then we discuss about this variable retention time, which makes the profiling actually so complicated. But then we discuss about this work avatar, that when we enable use of ECC with retention errors, and that makes it possible to implement it essentially. We're going to also see a similar work here that make it possible for this kind of profile. Okay. So let me quickly go over advantages and disadvantages. So upside, this reduces latency significantly and by exploiting significant within chip latency variation. But yeah, as an important disadvantage, need to determine reliable operating latency for different parts of the chip. So here we're going to have higher testing costs and essentially more profiling. And this will also result in more complicated controller. So in many of these techniques that we are discussing, we are actually changing the memory controller and making memory controller more complicated. And later on in today's lecture, you're going to see that actually memory controllers are already too complicated. So, but that's how it is. If you want to gain performance, there is no free lunch. You need to improve memory controller even more. So our goal here is that we should make memory controllers even more complicated, such that you can make it, you're going to have in the end more intelligent memory controllers essentially. Okay, so this is the paper, which if you want to learn, this is the paper, and also you can check the talks that we have had. There is also another work, Solar DRAM, which puts all these different idea, like the three first idea that we don't need to design for the worst case all together. I'm not gonna cover it. If you're interested, you can check the paper and also the talk that Jeremy has given. It's actually a very interesting paper to look, but we don't have time to go over it. Okay. So, so next we can actually ask this question that we have observed that we have this variation across within chip, but we can ask actually why we have such things. So the reason which is important to ask such question is that once you understand the reason, you can potentially design algorithms or techniques which is more which has a lower cost in the end. So that's why asking this question is very important. And then so you can actually get some insight from essentially from circuit theory. So if you look at this DRAM bank, which you're aware of this design already, we have word lines and also sense amplifier. So across the row, we have you're gonna see that basically we have different distance from the sense amplifier. So based on the circuit theory, those rows that they are further from sense amplifier, they're gonna experience longer latency. So so essentially this row is gonna be slower compared to these rows. Also, when you consider this decoder, when you want to access, basically provide charge for the access transistor, those columns that they are closer to your basically word line drivers, they're going to be faster. So with that, you can actually expect that we have inherently fast region in our DRAM chip, which is this corner, and also we have this inherently slow region in our DRAM chip, which is the further from the sense amplifier and also further from the word line drivers. Okay. So once we know this from the circuit theory, you can actually use this basically profile, use this actually insight in order to profile. So basically the idea here is that you can profile your DRAM chip for the inherently slow region because that part is smaller and you can test more. You don't have to profile for the whole chip. You start profiling for the inherently slow region and you find some timings for that. Based on your profiling, and then you're gonna use that timings for the whole chip essentially. So that's the idea here. So that's the work designed induced variation array or DIVA. So we have this inherently slow that we can provide only a slow regions to determine minimum latency that we can work on properly. And with that, you can have dynamic and low cost latency optimization. However, the problem is not that easy. So there are also some slow cells just because of the process variation. very similar to also the this variable retention time that we discussed, right? There are some variable retention time which you cannot control, and that can come and go at runtime. So here also we have some slow cells which can, they are here, they are in the DRAM chip because of the process variation. But the good thing here is that, I mean, not a good thing, but essentially the error that you're getting from these slow cells can consider them as random errors. But in inherently slow, those are actually more or less like localized error. So you can have that information. And then for this random error, you can apply error correcting code, which is a perfect match for ECC. Remember that for ECC, we talk about they are good for errors that we don't know the source of them, essentially, right? So these are slow cells, you cannot avoid them. I mean, they are in the chip because of the process variation. And for those, you can apply ECC just to make sure that you can operate properly. But for other basically cells, which you can understand the source of the error. So we know, because it's based on the circuit theory, we know that here is inherently a slow region, for example, in this DRAM chip, this DRAM bank, essentially. Sorry, not chip, actually, DRAM bank. Because in chip also we have different banks and also subarrays, essentially. So for those, you can actually, that these errors are localized, so you can actually operate, you can handle them by fixing the this TRCD latency, essentially. Okay, so that's how we combine online profiling and error correcting code. So by combination of error correcting code and online profiling, we can actually do this reliably and reduce latency. Yes.
Similar to what we had in the refresh.
So slow cells, I mean, aging can also affect, I'm not fully sure. In general, we have to do a lot more study on, different effects of aging, and I don't think we have done it. Because actually this analysis of aging also is very hard, the methodology is very hard. How to age your DRAM chip is a big problem. There are some, let's say, approximate methodology that people try to test aging by, for example, baking. They put the chip in an oven, on high temperature to simulate that aging effect. And for example, people have done it a lot for flash memory. For DRAM, I'm not sure if people have done that. So that's one thing. And also, if you want to test the aging also on real system, like on real scenario, you need to get some chips that they are aged. But then the problem is that you couldn't control the aging of those cells, because they have been used, for example, in some servers, and people have been using with different patterns, So the problem is that understanding aging is very hard. The methodology is very hard to do. So that's one thing. So I'm not sure, how would that affect here. But there are some slow cells that exist because of the process variation, Essentially those cells that, remember that when we want to access the cell, there are different parameters that affecting that access, right? We have this capacitor, which if your capacitor is small, you store less charge. And when you have less charge in your capacitor, that would affect the charge sharing process. You're going to have higher latency for that. And then also we have this access transistor and also the conductance. All these things can be different, right? When you when you fabricate, your fabrication is not perfect, essentially. So yeah, that's my answer. But whether or not, I mean, I think aging actually would affect, that cell, because aging is affecting. There are studies on, the latency effect of aging for logics, for example. But for DRAM, I'm not sure, but I think that would affect. I mean, my gut feeling would say that.
We would have a problem if a fast cell becomes a slow cell in the.
No. Fast, yeah, exactly. Yeah, fast cells can also become a slow cell. Yeah. Well, yes. Basically, you need to do this profiling, with periodically. I mean, if you cannot, you profile and you know that you have this inherently slow region, and then so based on that you get some numbers. But after some time, you need to profile again for that inherently slow region. But I understand what you're talking about. Like there might be some, let's say, not so slow cells, but after some time they may become slow cells. So with that, we are actually relying on ECC correction capability. If ECC is strong enough, hopefully that was fine. But yeah, but I understand. In the end, you know, that would limit the effectiveness. Exactly. Yeah. Yeah. Sure. Any other questions? Okay. So yeah, here are some results. So latency reduction for read operation with this adaptive latency DRAM, ALDRAM. Basically, depending on the temperature that you are working on, you can have different read performance. But with this DIVA profiling, one of the interesting thing about this is that it's actually almost independent of the temperature that you're working on. So even in high temperature, you can actually reduce latency a lot. And if you also read the paper, there is a technique about shuffling, which related to, you know, how to place things, you know, which might be also related to the thing that you also mentioned. So with that, you can actually also gain even more performance. And similarly for write, you gain very much write latency reduction. Okay, so I would say that one plus advantage about this work is that we automatically find the lowest reliable operating latency at system runtime. So essentially making this all these prior technique implementable, because those techniques actually they rely on very time-consuming profiling, which might not be really feasible at runtime. But this technique actually makes it possible because you have this inherently slow region, and you only profile for that region, and that region is small enough just to make sure that you can have reasonable latency for your profiling, essentially. And with that, you can actually enable that. And at the same time, relying on ECC is important because there are some cells that they are slow because of process variation, and using ECC makes it possible that you still operate on low latency. Okay, but disadvantage is that it requires knowledge of inherently slow regions. So that knowledge needs to be somehow transferred to the to our system from vendors, or also from from profiling that people have done. And it also requires ECC, which I mean nowadays actually we have on-die ECC on most of DRAM chips. And it imposes overhead during runtime profiling and more complicated memory controller. So like in the end, we are making memory controller more complicated and more. Okay, so if you're interested, there is a paper that you can also check, which provide more details about this work. Any question? Okay. Yes.
Know that in some cells, but I don't know if that paper has been tested actually on different.
So that was our profiling from. I mean, maybe in this paper also we reported, but in other papers we showed the the distribution across different parts of the chip, right? So we already showed that, but we didn't know the reason. So this paper tried to investigate what would be the reason, and one potential reason would be this inherently slow region that you might have. Yeah. Good question. Okay. So I think we have still time, so let's move on. So we have covered basically the first three, and we're gonna also discuss about how would change the supply voltage affect the the performance, and also about the application data. So I will I will defer the supply voltage to the later part of this lecture, but I will start with the application. I will continue with the application data. So this actually, I kind of foreseen it when I was answering to one of the question that essentially when you know your application, some part of your application error tolerant, you can actually map those part to the part of your DRAM, which so first of all, you reduce timing, so you violate some timing, and with that, you might actually impose some errors. You might cause some errors because of operating on lower latencies. But once you know about your application that some layers are more capable or they can tolerate some errors, you can actually map them on, let's say, more error-prone part of the DRAM. So this is the work that we have done for DNN inference, which basically deep neural network evaluation is very DRAM intensive, especially for large networks. And we have this basically that observation that some data and layers in DNNs are very tolerant to errors and reduce DRAM latency and voltage on such data and layers. And then we can, while still achieving a user-specified DNN accuracy, the DNN accuracy target, we can actually essentially improve performance. So data-aware management of DRAM latency and voltage for deep neural network inference. And that's the work, Eden. So here we basically we are reporting the maximum tolerable bit error rate for this ResNet for weights and input feature map. So IFM is input feature map. So as you can see that some parts basically you can tolerate around 2% error rate, but there are some parts of ResNet that for example you can tolerate more than 10%. So once you have this information, you can actually categorize it in different category, and you can consider now we have 4 DRAM partitions with different error rates. So one partition you can basically tolerate. You cannot tolerate more than 2% bit error rate. Another partition you can tolerate around 5% bit error rate, and 6%, and then less than 8%. So now you have these different partitions, and having this information, essentially you can map each of these partition to the corresponding partition in your DRAM, and then you can basically reduce latency and provide also better energy efficiency. But at the same time, you can still satisfy the accuracy target that you have for that DNN inference. So so essentially the goal is to enable accurate, efficient DNN inference using approximate DRAM. And Eden is an iterative process that has 3 key steps. So in one step, essentially, you have this DNN error tolerance characterization, which I already also showed you, the profile. And based on this analysis, you can map DNN to DRAM. And so after that, you get a final DNN and some accuracy target. If things are good, then we are fine. But if the accuracy target is still not there, we can actually retrain the inference. We can retrain the model considering those errors again. So this is boosting DNN error tolerance. People have done it also in different, in other domains, but essentially you can, retrain your DNN considering those errors to try to match, that target that you have. So that's a procedure which is kind of iterative. You need to do it until hopefully you get the, the output. Okay, so with that, basically we reduce DRAM energy consumption. You can see that on average 21% DRAM energy reduction, maintaining accuracy within 1% of original, assuming that 1% is still okay, And for the performance evaluation, we have, average 8% system speed up, and some workloads actually achieve much higher, like 17% speed up. Yeah, and with Eden actually, so here also we are reporting the, the result for the ideal case, which is, when we downscale TRCD to low numbers. So with that, ideally, if you can do that, of course, you cannot do it in real life because that comes at a low accuracy. But if you just do it to get some performance room, you're going to see that Eden achieves close to the ideal speed up, which shows the effectiveness of this technique. We also tested this idea for different host system. It doesn't need to be only CPU. It can be GPU operating on the DRAM. It can be some accelerators like Iris. It can be also TPU, like Google TPU. And all of them, we report different energy reduction improvements. And this is more about Eden. If you are interested, is the paper and also the talk that you can look at it. Which this paper also going to be part of reading as well. I'm not sure if we have mentioned it in homework 2 or later in homework 3. Do we have Eden in homework 2? But one of the suggested. So optional that you can review and get some extra credit. Okay. And just to flashback, I'm not going over these things again because we have already covered it. I think Professor Mutlu have covered in lecture 3, I guess, if I'm not mistaken. But this is very similar to that broader technique that to exploit memory error tolerance with hybrid memory systems. Remember that we discussed about having different application data with different tolerance, and then essentially we can have reliable memory and with that we map vulnerable data to it, and also we have low cost memory that we basically map tolerant data. And with that, we reported this idea of heterogeneous reliability memory, which I think you are aware of this, right? You guys remember? Okay. Yeah, I'm not going over it again. We have covered it. Okay, so with that, now we can discuss about supply voltage levels. So basically the idea is that we want to understand, basically to understand and exploit the voltage latency reliability relationship. So once from, I guess, some courses that you have in circuit, that when you reduce the supply voltage, you're gonna have longer latency, right? And when you also increase the voltage, you're gonna have less latency. So once you know that relationship in DRAM, you can actually also play with that, play with that voltage level and reduce latency, or maybe increase latency, but still operate on reliable scenario. So once you apply higher voltage, you reduce latency, and that can actually comes at a performance improvement, even though you're gonna also consume more power. But you can also do it in another way, like reduce voltage, and that gives you power efficiency, but also it comes at a longer latency. But hopefully we have enough slack in our latency parameters, which reducing voltage would not affect the performance overhead compared to the baseline, right? So this is the work that I'm gonna go over it quickly. This work actually we have done it with NVIDIA. NVIDIA back then, still also, they were quite concerned about the power of their DRAM because they do a lot of DRAM in their GPU. So they have done this work with us, and we built this, because we had that infrastructure that we could test the different DRAMs. And we use that also, we extend our infrastructure to apply this, have this DRAM power model. So essentially, we have a high DRAM power consumption in different systems, like in Power 7, which is more than 40% of the power actually comes to the DRAM. And in GPU also more than 40% also. So the key question is that how does reducing voltage affect reliability and errors? Because we know that if we reduce voltage, we can save some power. But we want to do it without causing errors, essentially, right? And how does reducing voltage affect DRAM latency? And how do we design new DRAM energy reduction mechanism? Okay, so we have this supply voltage control on DRAM that we can actually, change or tune the voltage using our infrastructure. And essentially, we use SoftMC back then to adjust the supply voltage to DRAM modules, and we schedule DRAM commands to DRAM modules. But this can be also done with our with the newer version of SoftMC, which is DRAM Bender. So that's why I'm also showing this here, that you can use this infrastructure to do this voltage variation. Later on also, we have done other kinds of voltage variation in DRAM, like changing the access transistor voltage to show the effect of it on RowHammer, for example. So you can do a lot. We can have a lot of fun by changing the voltage, different voltage in DRAM, and see the effect of it. Okay, so we have tested 124 low voltage DRAM chips, DDR3L, and in this low voltage they operate nominally on 1.35 voltage. However, commodity DDR3 actually they use 1.5 voltage, so that's why they are like low voltage. And yeah, and then we iteratively basically read every bit in each 4 gigabit chip under a wide range of supply voltage levels, and we sweep voltage level from 1.35 to 1 volt, like 26% reduction in supply voltage. So we couldn't. You can also think of reducing more, but at some point, when you reduce the voltage more, it's not a matter of how long you wait. If you wait also infinitely, you may not get the results because the circuit may not operate properly at some point. Because you need to also consider the threshold voltage, for example, right? And so you cannot, for example, go less than threshold voltage. Even though there are some also architecture, they all have this sub-threshold, which you might be aware of them, but those are not also applicable much in DRAM technology. Okay, so here are the results. Basically, the nominal voltage is 1.35, and then we reduce supply voltage, and we are reporting 3 vendors. So that's the profile, and so the y-axis is the fraction of cache lines with errors, essentially. So in vendor C, we observed that, for example, we can. So vendor C, actually, we were not. Is much more sensitive on the voltage. So when we reduce nominal voltage to 1.3 and more than that, actually we observed errors. So with vendor C, actually you are not lucky enough, so you cannot reduce nominal voltage a lot. But with other things, with vendor B, for example, you are much more tolerant. So until 1.15, for example, you could reduce supply voltage without observing any error, and after that you're gonna start observing errors. So we are observing heterogeneity again in this kind of analysis as well. Okay. At the same time, also because we wanted to understand this more and we test more data, we also develop a circuit model using our profiling result, and we tune this circuit model, which is you can actually get also this from our GitHub. You can run it, for example, using tools like HSpice, LTSpice, if you are aware of those tools. But essentially, you can do a lot of circuit simulation with this circuit model. This model is actually one a DRAM cell with a bit line and also sense amplifier. And you can combine it to make bigger rows and columns of your data. So with our SPICE simulation, with our circuit model simulation, we observe that here is the result, that once we reduce supply voltage from nominal voltage, we actually have higher latency in accessing our DRAM cells. So with activate and pre-charge, essentially we are observing this. So at some point, when you reduce supply voltage more, you cannot operate reliably on the latency parameter, or let's say the latency parameters that vendors have defined. Meaning that if you want to operate and you want to reduce supply voltage even more, and it still doesn't see errors, you need to essentially wait longer. So you need to operate on higher latency parameters. But as I said, at some point, reducing supply voltage more than that would not, I mean, it's not possible because the system, the circuit would not work anymore. Okay. So essentially we also tested this kind of latency profile. So this latency profile is coming from the circuit simulation, but also we get this from our real analysis, and this real analysis also kind of shows the same trend with our circuit simulation. But you can see that. So here we have different supply voltage, and on the y-axis we have measured minimum activate latency. So this big circle one means that all the DRAM cells working on this supply voltage, which is the nominal voltage, basically they can operate on this latency 10 nanosecond reliably without observing any errors. So when we reduce essentially the supply voltage at some point, at this moment, 1.10, you can see that 90% of the cells, they could operate on 10 nanosecond, but 10% of the cells, they need longer latency, for around 12 nanosecond, for example. And reducing more, you can see that, for example, 50% of the cells, they could operate on 10 nanosecond. 40% of the cells, they could operate on something around 12. But 10%, like they were gone. They couldn't, you could not operate on them reliably without, I mean, no matter how long you wait, essentially, because that's a new supply voltage for those cells is just too low. And as you reduce supply voltage more and more, you're going to see this effect more, like having something around 1 volt, only 10% of the cell would work, and 90% of the cells, they don't work. So this profile from real analysis on one DIMM actually also shows similar trend, of the similar trend that we have also observed with our SPICE simulation. Question? Okay. So here also we have this kind of special locality of errors. So across different banks and different rows, actually, you can see that we have kind of a special locality. So there are, when we have 12% voltage reduction, there are some banks that they can actually operate reliably, but some banks actually they have errors. And in those banks, actually, you're also observing a profile depending on which row you're operating on. So having this kind of information also would benefit us to, to design better techniques. So errors essentially concentrate in certain regions. So with that, we propose a Voltron that essentially, basically user specifies performance loss target. Like, for example, user tells you that I can tolerate 5% reduction, 5% performance reduction, save as much as you can power, and then you can apply Voltron. And then you essentially reduce supply voltage and also tune the latency parameters such that you can still operate properly within that lower supply voltage. But hopefully, basically, we need to make sure that we don't violate that performance requirement that we have. So that's the idea that we are considering here. This is one way of thinking about it. Also, there are systems that we have. Remember that we discussed about low latency architectures and also predictability, right? So in some systems, actually, you have some average performance that you want to, you have, but the most important for you is that you want to be predictable, in terms of latency. For example, the execution time, you want to be, done with your application in less than, let's say, 15 milliseconds, for example. But on average, your actual execution time is around 5 milliseconds. So now you have a slack time here, and then you can play with that slack by applying such techniques. And people are also doing it in different systems. Like by doing this, if you know about it, like dynamic voltage frequency scaling. you dynamically scale voltage and frequency of your hardware architecture. So with that, you are reducing performance, but hopefully you won't violate the deadline that you might have in your system, right? So there are many applications actually that they have such kind of requirement that you can actually play with the performance, still satisfy the goal, because you have a deadline and you need to make sure that you don't violate the deadline. So that's for sure. But you can apply such techniques, and within that deadline, you can reduce power consumption and energy a lot. There are also some other applications that they allow you actually playing with performance. You know, you have some soft deadline and also hard deadline. You can play with soft deadline a little bit, like lab, submissions that they have soft deadline. So you can, people can play with that soft deadline and impose some performance overhead, but still within that provide a lot of energy efficiency. So I'm just giving those contexts to you, just to understand that saying that, oh, I can tolerate 5% performance reduction is not something that, is so weird. Like people are also actually looking into that. There are many applications that you can actually have such things. Okay. And yeah, that's about it. So now the question is that how do we predict performance loss due to increased latency under low DRAM voltage? And for that, we actually devise a model. We use a linear regression model. I don't think that's the best model. So there are actually room to do much better. Back then, we used this linear regression to model that basically performance overhead when you increase the timings of the DRAM accesses. But I think nowadays we can actually also use more sophisticated models. Some machine learning model could also help here. So essentially, this model, we input applications characteristics and different DRAM voltage. And essentially, the output of the linear regression model is the predicted performance loss. And with that, basically with the target that we have, the target performance loss that we can tolerate, we can actually get the final voltage, that we can operate on it. So that's the idea about it. So here is the result, which we compare against one of our prior work, which is memory dynamic voltage and frequency scaling, which we have done it actually on memory bus. I don't have time to go into detail of it, but compared to this MEMDBFS, actually Wortron provides essentially energy saving quite a lot for low and high intensity, memory intensity applications. And here also we are showing our performance target. So we wanted to have at most 5% performance loss. And we observed that actually with Voltron, so the good thing is that we are not violating 5%. But you can see that actually our model is too conservative. So for example, here we have, around, let's say 2% performance loss, but we could tolerate 5%, right? So there is, of course, room for designing more accurate and more accurate model, such that you, in the end, you can save more energy, essentially. Makes sense, right? Yes. I don't remember, actually. I mean, I don't have it on the top of my head. I'm not sure if the paper actually talks about it, because that regression model, you can actually do it offline, and then based on that, you can use it. But you're asking about how often we retrain that regression model, right? I'm not sure, yeah. Other questions? Okay. As upside, Voltron can trade off between voltage and latency to improve energy or performance. We didn't show about, how can we improve performance, but as you know, like increasing supply voltage would cause lower latency. So you can also play with that to improve performance at the cost of some energy. And Voltron can exploit the high voltage margin present in DRAM. But this requires finding the reliable operating voltage for each chip, which is, again, higher testing cost, and again, more complicated memory controller. So if you want to learn more, you can actually also watch this talk that Giray has given in Actually, one of the the past edition of this course in fall 2019. So yeah, but I don't think we're going to cover it this time in our cutting edge presentation. Okay, question? If not, I think it's a great time to have some break. Let's be back at 2:25, and we will continue with the rest. Thank you. Okay, let's continue. So we discussed about reducing memory latency for improving performance and better energy efficiency. But you can also think of reducing memory latency to support security primitives. And this is something that you actually kind of seen in previous lectures on processing using memory. That, for example, we talk about when we reduce the TRCD, there are some cells that they fail randomly, and you can use those cells as a primitive to generate random numbers, and those random numbers can be used for security reasons. Or, for example, regarding that physical unclonable function that we discussed. But I'm going over some of these techniques. So the first category, that generating two random numbers, we actually have covered it more or less. So I still have slides about it, but I'm not gonna go over them again. So it's just for you to to check it at home if you want to get more information. But essentially we discussed about all of them, like DRAM, QuARCH TRNG, and PyDRAM, like we have covered it before. So I will start with the second category, which is evaluating physically unclonable function using DRAM. This work also we discussed about it, but very briefly. So now I will provide a bit more information about it. So this is the work, DRAM latency PUF. So basically the motivation is that we want a way to ensure that the system's components are not compromised. So you can use this physical unclonable function, which sounds like a very fancy name, but what it means is actually you have some signature on that device, and you use that signature to trust essentially your component. So that's how PUF. So you can also think of adding some hardware circuits, into your chip, and with that hardware circuits, you can you can query that, and based on some agreement, you get trust or not. But in order to improve the security, actually, people have considered things that they have some variation. So that's why physical unclonable function that they are based on some variations, they are actually much more interesting. They are very hard to imitate, and such that you have a device, and so there might be some intermediate devices such that they imitate what you're getting from that device, and give you that trust. But with this variation aware physical unclonable function, it's very hard to do that. So that's why people have looked in it in more detail. So yeah, so we refer to the unique signatures as a PUF response, and it's often used in a challenge response protocol. So we have this that essentially you challenge. I will show you with some picture, but you challenge with your device, and that device provides some responses. And with that challenge and response, you can actually trust your device or not. So this is a trusted device, and this is the device that you don't know if you want to trust on it or not. So you basically send the input challenge X, and this device would evaluate the PUF and reply back with the response of that PUF. So basically we check the PUF response, and if it's correct, then we consider this device as authenticated, meaning that, okay, now you can trust your device. You can write, for example, your data. Essentially, you can work with this device now. So that's PUF. We want to have a runtime accessible PUF that should be evaluated quickly and with minimal impact on concurrent applications. And we want to protect against attacks that swap system components with malicious parts, essentially. So DRAM is a promising substrate for evaluating PUF because, I mean, it's everywhere in modern systems. So if you want to, as one of the important components in your system, when you want to trust, you also need to trust your DRAM. So that's why In this work, we focus on POF. There has been work actually on providing DRAM POF, but they are actually unfortunately slow, and they can get exponentially slower at lower temperatures. Like one of them is actually based on retention time. You can actually imagine what would be like you have, based on the retention time profile of that DRAM, you can also generate some POF. But remember that first of all, it can be not that accurate because of that variable retention time that you might have. In latency, we don't have that kind of variable, that quantum effect that would affect different latency. But in retention time, we have that. So that would affect actually the accuracy of your POF. But another problem is that in lower temperature, actually retention time can actually go to high numbers. Like you can actually have a retention time of few seconds to few minutes actually, or even longer if you operate on very low temperature. So that's why actually this evaluating POF can be exponentially slower at lower temperatures. So basically we wanted to do that on a different way of doing, providing POF. So effective POF characteristics, first of all, it should be repeatability. It should provide repeatability, meaning that you can actually, doing it repeatedly and get a similar challenge and respond. So different, every time you send challenge 0, for example, you get POF response of 0. So that's important. Another important thing is that it should provide diffuseness, which you provide different challenges, like challenge 0 to n, and you need to get different responses. So these POF response should not be similar. And also we need to have a uniform randomness in our POF characteristics, such that people cannot learn from how you are generating response. Essentially, if you don't have randomness, people can try to use multiple challenge response pairs to guess, another. And it should also provide uniqueness. Like if you provide a challenge Z to different DRAM devices, you need to get different POF response. So that's one of the core, such that you can rely on your DRAM chip. And it should be also, you should not be able to clone it, essentially. So like with DRAM POF, basically, you cannot clone it, right? So there are a lot more in the paper. If you're interested, you can check. But essentially, runtime accessible POFs must have low latency. So each device can quickly generate the POF response, and low system interference. So it should not interfere with other things that the system is doing. So POF evaluation minimally affects performance of concurrently running applications. So you know about the idea, the key idea of this DRAM latency POF, because we already discussed it. But essentially, there are some cells that they are so weak, and they have high percentage of chance to fail with reduced TRCD. So we discussed about when we reduce TRCD, there are some cells that they don't fail because they are strong. There are some cells that they may randomly fail, and you can use those cells actually to generate random numbers. But there are also some weak cells that they always fail, when you reduce TRCD. So those weak cells actually can be used to generate POF, essentially, for that. Okay, so the key idea, again, this work is to compose a POF response using the DRAM cells that fail with high probability, essentially. So as an important result, we can evaluate the DRAM latency POF in only 88.2 milliseconds on average, regardless of temperature, because of some specific mechanisms that we have in this paper, which you need to check the paper for more detail. But here are the results. Compared to prior work with DRAM retention POF with different manufacturers. So this work, DRAM latency POF, is always 88.2 milliseconds, regardless of the temperature that you are using. But DRAM retention POF actually, so first of all, it's actually very different. First of all, it's very slow. You can see that like 2 orders of magnitude different. in the latency. And also you have a lot of variation in terms of different manufacturers and also different temperature that you're operating on. So when you're having lower temperature, you're going to have basically you need to spend much more time in evaluation of this PUF. So DRAM latency PUF is fast and constant latency, and on average, 2 orders of magnitude faster than the previous DRAM PUF with the same DRAM capacity overhead. Here also the executive summary of this work, which I'm not going over it, but you can also check later. So if you're interested, is a paper that you can check, and also the talk that Jeremy has given, the first author of this work some time ago. Question? Okay. So if not, then I will continue with this generating true random numbers. As I said, I'm not gonna cover it in detail. We just have the slides for you to check, but we can use this idea of reducing TRCD, and that there are some cells that they fail randomly. If you remember this plot that we had. So we have this guard band, and when we reduce TRCD, depending on have the strong cell and weak cells, some cells that they are weak, they always fail, but there are some cells that in our guard band, they may fail or they may not fail. So those cells actually can be used as a random number generations, like here. So these cells that they stand here, they may fail or they may not fail randomly, and then you can use them. So yeah, I'm not going over it again because we have discussed it. And later on also we use this TCuARCH TRNG that we can essentially activate 4 rows in DRAM, and that provides random numbers. You can collect random numbers in the row buffer, and then you can use it essentially for random numbers. Okay. In our recent work also, you remember that we can now SMILE has shown that we can activate much more than 4 rows, right? So there is also a recent work that we are is going to appear in ICCD. Which we show that how can we use multiple row activation, not only 4, to generate random numbers. And it's very interesting also to see the trade-off there, because if you remember, when we increase the number of rows that we are activating, you are increasing the entropy, which can help you to generate random numbers with higher throughput. But at the same time, activating more rows at the same time would basically cause longer latency. So that can affect the throughput that you are getting from your random number generators. So in the end, it's a very interesting trade-off that we are discussing in that paper, which we may actually discuss it at some point in this semester, or we'll see. Okay. And yeah, a lot more work on that line, like designing a system, an end-to-end system around random number generations, and this PyDRAM that we actually tested on FPGA-based framework, on real system. Okay, so that's about this category about generating true random numbers. Are there any questions? Okay, now we can actually move on to the third category, which is quickly destroying in-memory data using DRAM. This actually, we also discussed it a little bit, I think last week, if I'm not mistaken. We discussed about this retention time, and say that when we cool down the DRAM, actually retention time can go, can be much longer, right? And I talk about this attack, which is called cold boot attack, that if an attacker has physical access to your system, they can, for example, cool down your DRAM with, I don't know, nitrogen liquid, for example, and that would make your DRAM, in quite low temperature. And in that temperature, actually, you can basically, retention time can go to several seconds, several minutes, or even more. So with that, they have enough time to detach the DRAM, the DRAM DIMMs actually from the system and put it in another system, and they start reading your data, right? So that's cold boot attack, and people actually have looked into it by using by addressing it with encryption. Like so, you have an encryption key, and whenever you want to write to your DRAM, you encrypt your data and you write it to DRAM. And that key is actually stored in somewhere, not in DRAM. So such that if someone just gets your DRAM, they're not capable of understanding that. But there are ways to also do some reverse engineering and get the key. So there are a lot of work on that also in that line. But I remember, I can share you a very interesting story. I remember that we were discussing actually those papers that people try to avoid cold boot attack with encryption in a reading group. In yeah, sometime if I'm not mistaken, in May 2017, around that time, May or June, yeah. And we were discussing, and then Louis, actually, the first author, he spoke up and said that why not having a DRAM that when you put it on another system, that DRAM starts destroying itself, And it sounds naive, but actually it sounds so effective, And that, message, the idea was the core of this work that we started, working on it. I remember we first submitted this work to HPCA 2018, but didn't get through. And I think in the end, if this paper got accepted after 8, if I'm not mistaken, 8 rejections. So initially the work was named Data Plant, but after some time, we actually improved this work, and this gets to a framework which you can do a lot more. You can avoid cold boot attack, but you can also do something else in that work. So I'm not going to go to a lot of detail of this work, Codic, but this is the work that finally got accepted in ISCA 2021. You can see that we submitted in HPCA 2018, and finally it got accepted in 2021. So a lot of resilience is neat, for such things. Talking about being review process and resilience, Professor Mutlu in Micro, he did a keynote about research. I mean, some cutting edge research that we are doing, like in the line of memory-centric computing and also in RowHammer. But through that talk, also he discussed some things about review process and how reviewers should behave. Actually, they should behave in just to make sure that we are advancing the science. That should be the goal essentially. So I recommend everyone checking that talk. I will put the links in the after lecture slides. So if you're interested, you can also watch that. Is it 1 hour? More than the whole, but the segment is that's no, the whole. I mean, the initial part is not like we started live stream, I think a bit early, but yeah, it's around 1 hour or so. It's around 1 hour or so keynote talk. I mean, I have listened to a lot of talks from Professor Mutlu, so I know most of them, but this talk, actually, I watch it on YouTube at 2 a.m. Because the conference is happening in South Korea, so we have this time zone difference. And I loved it. I loved it, actually. It was very exciting. So I recommend everyone checking that keynote. Okay. Yeah, so that's the site. This codec, which I will try also to go over this long executive summary, let's say. So the problem is the timing of internal DRAM operations is fixed, which hinders the potential of DRAM for implementing new functionalities and optimizations. So that's, about it. So the goal in this work is that we wanted to provide control over DRAM internal circuit timings to enable new functionalities and optimizations. So we devise a codec substrate. The key idea is that to enable fine-grained control on fundamental DRAM internal circuit timings. That control key basic components in the DRAM array, like word line, sense amplifier, pre-charge logic, and so on and so forth. So just to give you a bit more context here, for example, when you send the memory controller sends activation command to the DRAM, but that activation command involves first that word line activation, to connect that transistor. Sorry, to connect that capacitor DRAM cell with the bit line to do this charge shading. And then at some point, we basically we need to enable sense amplifier, right? But in DRAM controller, you don't send basically word line activation, and also you don't send sense amplifier activation command. You just send activation commands. But there are some internal circuitry to do that you do basically word line activation and then sense amplifier activation. So if we can provide those kind of information, those control essentially to the outside the DRAM, you will be able to do much more internally inside the DRAM. So we propose and evaluate two codec variants, codec SIG, which to generate signature values, which you can use it for Prof, and codec det, which deterministic, generates deterministic values. And we use this, for example, to essentially you can write some deterministic value. So you can use it for destroying your DRAM. For example, write all 0, or you can also use it for initialization of your DRAM. For example, there are some parts of the application when you want to start, you need to initialize, some rows to some 0, for example, you can do that. Okay, so yeah, and these are more information about codec that we use for Prof and also for cold boot attack, which I don't have to go over it, but essentially the key idea is that destroy all data at power on using codec. So when you put DRAM on put your DIMM on a system, there is this power on process, such that memory controller starts understanding that, okay, this is my DRAM and I can communicate with that. So that power on process, you can actually destroy everything using this codec technique. So yeah, so I'm gonna explain this work a little bit on some of these slides that we have. So first of all, this is Luis. He was a postdoc in Safari, but now he's a director of supercomputing in Galicia, if I'm not mistaken, in Spain. But essentially, you have these internal DRAM signals that word line controls the access transistor that connects the cell capacitor to the bit line. Sense amplifier also, you have two separate activation signals, sense P to activate this PMOS and sense N to activate this NMOS. And also you have this equalizer signal to basically which used for pre-charge circuitry, just to make sure that both bit line and bit line bar, they are basically they have a similar voltage, VDD over 2. So all these internal signals that we have in our DRAM circuitry, they are not exposed to outside DRAM. So you cannot, for example, send a word line command, or you cannot say sense P, for example. But if you have control on all these internal signals, you can do something interesting. For example, what you can do is in order to generate POF, for example, you try to write VDD over 2 on your cell. So first of all, you pre-charge your bit line to VDD over 2, and then so you and for DRAM cell capacitor, you also activate it. So essentially, you activate. This is the word line. So you activate after 5 nanoseconds, let's say, and this capacitor starts to do some charge sharing with the bit line, right? So that's a normal procedure that we do. However, if you keep the equalizer signal also active, that means that your bit line is connected to, while you're doing charge sharing, that bit line is also connected to VDD over 2 power supply. So in the end, your bitrame will converge to VDD over 2. And since the capacitor is also connected to the bit line, because we keep this access transistor open, that capacitor will also get to VDD over 2. So remember here, we don't do only charge sharing, because when you do charge sharing, that capacitor, because it was 1 in the beginning, capacitor will get some perturbation and gets a little bit higher than VDD over 2. And then bit line also gets a little bit higher than VDD over 2. And then you have this sense amplifier that you can sense. However, here we don't activate sense amplifier at all. By keeping the sense PMOS at high and also sense N at low, meaning that sense amplifier circuitry is not activated. However, the pre-charge circuitry is activated because we activate this equalizer signal. So with that, you can actually write VDD over 2 in that cell. Make sense? So you write VDD over 2 in that cell. That's the result. And in the next activate command, which you can do it actually essentially normally. So in the next activate command, since that cell actually has VDD over 2, then the sense amplifier would generate a signature value that depends on truly random process variation. And you can use that for Prof in the end. Because a sense amplifier would generate deterministic value if you have 0 or 1 in your cell. But if you have VDD over 2 in that cell, that sense amplifier would also generate random numbers. I mean, it would basically generate something which is depends on truly random process variation. So that's how we can use it, for example, for generating POFs. Similarly, also you can think of it how you can use it to destroy your DRAM, essentially. By controlling sense N and sense P, you can write deterministically 1 or 0 in the cell. But to know more information, you can check the paper and also watch the talk. Question? So another way of also doing this, basically this destruction, when you want to destroy your DRAM, is to use in DRAM multiple row copy. So you can actually think of, okay, I have when I want to essentially when I want to destroy my DRAM, like destroy the data, which is sort of not destroy physically. You have some, you write, for example, full 0 and 1 row, and then you quickly copy that row across many rows. So back then we didn't have that insight that we can do multiple row copy using techniques like SIMRA that we proposed recently. So we compare these coding techniques with row clone. That essentially, if you want to do that, you need to copy. You need to do a lot of copies. Like you copy 1 row to another one, and then another cycle you can copy another one, and then another one, and another. But you can also think of doing it basically kind of in parallel by copying 1 row into multiple rows using techniques like SIMRA. So there has to be interesting study that which one is faster, doing this multiple row copy or using codic, substrate to destroy the DRAM data, essentially. But we have not done it recently, still. Okay, so yeah, this is what I discussed about it, like row clone and multi-row copy that you can do with this work, SIMRA, that the Smile has led this project. Okay. There are also some works on reducing refresh latency. We have discussed about, how we can parallelize refresh access with some other accesses, if you remember, which can provide performance improvement. But there are also some works on reducing the latency for refreshing, which I don't have time to go over it. But if you're interested, you can also check this paper. That's basically to reduce refresh latency. Yeah, so you can also reduce memory latency by exploiting memory access patterns. There are different works on it, but one work that I want to describe it a little bit in more detail is this work, Charge Cache, that Hassan has led it. So it's very interesting, essentially. So the goal here is that we want to reduce average DRAM access latency with no modification to the existing DRAM chips. The observation is that a highly charged DRAM row can be accessed with low latency. So when you have basically you write your DRAM row and you don't access it for a while. So basically you are spending on retention, right? So that DRAM cell may not be fully charged. So the observation here is that when the DRAM row is not fully charged, meaning that like we have written some time ago and we didn't get to the refresh interval yet. So we have lost some essentially some charge. So with that, you have actually much less slack in in tolerating lower latency because you have less charge. However, the observation is that a highly charged DRAM row can be accessed with low latency. So if we know that that row is highly charged, you can actually potentially reduce the latency for that row more. And we know that also a row's charge is restored when the row is accessed through this charge restoration process. Then we can actually conclude that a recently accessed row is likely to be accessed again. Sorry, this is also another observation, which is kind of insight, that we have kind of locality that is recently accessed row is likely to be accessed again, row level temporal locality. So now the key idea here is that to track recently accessed DRAM rows and use lower timing parameters if such rows are accessed again. Because you have accessed these rows recently, you already restored the charge in those rows, so they are fully charged. So if you access them again, in a limited time period, you can actually access them faster. So you can actually operate on lower timing parameters, essentially. Yes. RowHammer? No, it's not related to that. In what sense it can be? Yeah. Well, okay, I understand from which part you're talking about RowHammer. So you're saying that, okay, I access a row, and in near future, I will access that row again. So if I re-access that row frequently enough until we get to the refresh, we might induce some RowHammer errors. Yes. Well, yes. But that's another thing. But you can do it maliciously. So here we don't necessarily think about doing it maliciously, that you keep accessing a row, frequently. Just in normal operations, you access a row, and then in between you access some other row, so you close that row, so you need to activate it again. But since we have already recently accessed that row is fully charged. So when I want to reactivate it again, I don't need to spend a lot of time to reactivate. And so I can basically operate on it with lower timing parameters. Make sense? No, pre-charge is still required. Pre-charge is required because you need to pre-charge the DRAM bank to. Otherwise, you cannot work with the sense amplifier, because sense amplifier needs to observe that perturbation on bit line. But no, what I'm saying is that remember that we were discussing about capacitors, that how much charge they have. Exactly. So if that capacitor has enough charge, that procedure can be faster. Yeah. So that's charge cache, which is low cost and no modification to the DRAM, and provides actually higher performance and also lower DRAM energy consumption. So more on charge cache, you can actually check this talk from Hassan in 2018. Yeah. I should also say that we have. Let me finish. Yeah, we have done also some other works on this line. This partial restoration of cell charge, which I don't have time to go over it. Also, parallelizing refreshes and accesses that we actually have seen it in our retention lecture, data retention lecture. And this work from Giray in Hira, which we showed that we can do it in real DRAM chips. Okay, yes. Memory controller, yes. I mean, that's a tough question to answer. I mean, I'm not sure about fundamental reason, because some of these are not really fundamental. There might be, a lot of business reasons, involving here. First of all, you should understand that DRAM controller is part of the CPU chip now. Yeah, but so like DRAM companies, like DRAM vendors, they don't have a lot control. They just provide, the timing constraints that DRAM controller needs to obey. But in the end, the processor chip should decide to implement that. And some of this, the idea that we have discussed here is actually making DRAM controller more intelligent, meaning that actually we are going a little bit away from processor-centric mindset, which might not actually work in a business model of designing processors. So I'm not really sure about so because some of these actual things are not really fundamental. They're just some decisions dictating by some, by vendors and by business markets essentially. But there are also some reasons on that, like memory controller is a tough module to design to begin with, And when you want to make it even more complicated, you need to rethink the whole system, because that's not easy to do, because you have huge design space exploration. Okay, what to include in your DRAM controller, what not to include. So like the problem is not easy also to solve. I'm not sure if I answered your question, but what I'm saying is that partly is not fundamental, because it's just some decisions from companies, but partly also is a bit fundamental in the sense that designing DRAM controller is not easy. I think you remember when Professor Mutlu was describing his story from Chuck Tucker, right? The person that he won Turing Award in 2009. You guys remember or not? So then maybe I will also talk about it again when we start memory controllers. But essentially, Chuck Tucker also was saying that memory controller was one of the hardest thing, or let's say the worst thing that he has designed in here. Even though he has a lot of experience in designing. Like he won this Turing Award because he was pioneered in the personal computing and the modern personal computers, let's say. And also a lot of works that he have done in tablets and in Microsoft. But in DRAM controllers, actually, he was also complaining a lot. Yes. Yes. Kind of IP, yes, but what do you mean? So essentially, the main reason that, we will discuss it actually more when we start memory controllers today. I hope so. Actually, we will start. But yeah, we will start, I guess. So, but in memory controllers, actually, we have. So the one part of it is actually doing signaling, like analog to digital and digital to analog, and that's a very tough part to do. To make it possible to operate on high frequency is very hard to do. And the rest of also other parts of memory controller, you need to do a lot of decision. And that when you want to do that decision, design space is so large, which can cause a lot of complexity. And now we are saying that we need to also add more to that memory controller and make it even more intelligent, you know. And
There's some like
yes, yes.
I wonder
Make it better what? But people have working on the improving memory controllers, of course. But I should also say that we didn't give enough justice to memory controller because people actually, you know, focus much more on processor chip or processor die, you know, through this processor-centric mindset. Yeah, that's better for business probably, but not for science maybe. And you know, evolving in our computer system. But we will get back to that when we start memory control lecture. Any other question? Okay. So we also discuss about, you know, how we can use this, you know, the voltage latency variation to reduce power consumption, and that's also all these techniques. We also devise a DRAM power model, which can be also used in such cases for better studies. This work, Vampire, is one of the, but we also, but that, you know, this needs to be done more now with more recent DRAM technologies and interfaces. Yeah, this is the, you know, the power measurement platform that we have designed back then for DDR3. And yes. Okay, so let me conclude this lecture, and then we can take some break. And after that, we get to our ambitious plan. Okay. So we wanted to have fundamentally low latency computer architectures, and we discussed about, you know, two reasons that we don't have you know, low latency memory accesses like DRAM accesses, and we tackle actually both reason one and reason two with different techniques. So there are a few takeaways that I want to mention to conclude. So first of all, we can reduce memory latency with change of mindset. Like most of these techniques are actually implementable. We just need to, you know, think a little bit differently what we want to prioritize essentially. And main memory needs intelligent controllers to reduce latency. And our DRAM controller, memory controller that we use for DRAM is not really that intelligent. It just makes it possible that you work with that DRAM, but that's a hard thing to do also to begin with. But that doesn't mean that you cannot do more. And if you know later on, also you will know more. But the controller that we use, for example, for flash memory, they are much more complex, and they are much more intelligent. And so there is no reason that you should not have that kind of controller for DRAM as well. So we use different principles actually in the solutions that we provide. So that's why actually these solutions are not only limited to DRAM technology. They can be actually based on, I mean, applied to other memory technologies because they are kind of principle design. Remember that we use a lot about these two principles: better than worst case design and heterogeneity, which actually you know, provide a lot of performance improvement for us. But these ideas are applicable to other technologies, like we will see also later when we talk about flash memory. Like this work, you know, consider that similar ideas to what we have discussed for flash memory, and also on phase change memory PCM, you can apply these different ideas. Okay, and that concludes memory latency lectures. Okay, let's take another 15 minutes break until 3:25, and we will continue with memory controllers. Okay, so let's continue. Is all good on YouTube and Zoom? I hope. And I'm still audible, right? Okay. Okay, let's hope for the best. Okay, now we can actually continue with the second part of today's lecture, memory controllers. Clearly, we won't be able to finish it. That would be too ambitious. But tomorrow we will continue and get to more also exciting topics on memory controllers. So the thing is that so far we have discussed about memory controllers a lot. Like in many of these works also we discuss, okay, you know, how we can change memory controllers to support this technique. But this lecture actually essentially tries to, you know, provide more detail about memory controller. Why is it that hard to implement? Why is it that important? And so you're going to learn a lot of details about memory controllers. Yes. And as I said, I mean, memory controllers is one of the important part of the system that people didn't put enough justice to it, unfortunately. Partly because of, you know, that processor-centric mindset, which is still a major mindset in our community. Okay. So, but essentially, just to go quickly over it, it does. So we also need memory controllers for other memory technologies. I will first also go over some other stuff very, very quickly, and then we get to the DRAM controllers. So long latency memories have similar characteristics that need to be controlled. It's not only DRAM, like there are also flash memory. They have a lot. So we will use DRAM as an example here, but there are you know, other memory technologies that you need to control them essentially. Flash memory, emerging memory technologies like phase change memory, STT-MRAM, and other things. And these things, the things that the other memory technologies, they have different characteristics, and they may actually add or remove some of the, you know, some of the job of the memory controller. Like for example, some of these memories are considered as non-volatile, meaning that ideally, I mean, non-volatile does not mean that necessarily, but ideally they can retain the charge, or let's say they can retain the value that you have stored to them for an infinite time. So you don't need to refresh them, for example. So one of the job of DRAM controller is to refresh DRAM, for example, right? But STT-MRAM, for example, or PCM, for example, they are capable of storing you know, the data for a long time. So you don't need to refresh them you know, necessarily. Flash memory also, you don't need to necessarily refresh, but we have shown, other people also shown, that if you don't do refreshing in flash memory, at some point, you're gonna see a lot of retention errors. So you need to still do some refreshing, but much less frequently. For example, every week for flash memory. But for DRAM, for example, every 64 or 32 milliseconds. So that's the difference, right? So there are different characteristics here. And when you design memory controllers, you need to consider these different characteristics of that specific memory technology to support it. Another important also insight here is that some of these memory technologies, they have program and erase cycles. So they have limited endurance. Like in DRAM, for example, we don't, I mean, so far we haven't observed endurance problem. So you can use your DRAM for a lot of time. But some memory technologies, they have limited endurance, meaning that they can tolerate or afford a limited number of program or arrays. If you write, for example, to those memory technologies or memory cell more than some amount, that cell may not operate properly anymore. So you cannot read and write to that cell reliably. So that's the program arrays, for example, cycles. So in order to increase the lifetime of that memory technology or memory chip, people need to level the wear of the chip. You know, you don't want to wear out one cell quickly while other cells are still alive and, you know, young. So people try to use some techniques like wear leveling to age or wear basically the whole chip in a balanced way, such that you can have a longer lifetime. So that's also one thing that, for example, memory controller, specifically, for example, for PCM or flash memory should do. But for DRAM, for example, we don't care about that things, for example, right? So there are also other examples which I don't want to, because at some point it's going to be boring. But there are many examples like that that you can think of, you know, how you can specify and customize the memory controller based on the technology. So as I also foreseen also a bit before, flash memory, they also have controllers. Flash memory controllers also considered as SSD controller in general. And so they are flash memory specific. There are a lot of actually unique characteristics in flash memory. And the goal for that flash memory controller is to, first of all, handle all these characteristics, and also make sure that these unique characteristics are not exposed to outside the system, to the host system. Because the host system, for example, the whole system are you know, are optimized or designed to work with hard disk drives. And if you can attach some SSD on the system, you don't need to, for example, change your, you know, the processor. You don't need to change the program. You can just benefit from that SSD, assuming that your motherboard, you know, provides that possibility. It's true that if people try to improve the operating system and other stuff in the system to benefit from SSD, you can gain much more performance. But ideally, you are capable of just applying SSD on your system and that benefit from SSD. And that's the job that from SSD controller, because SSD controller actually tries to hide all these you know, unique characteristics of flash memory. And essentially, the view of SSD from the OS level and internally from the SSD level is completely different. So OS still sees SSD as a flat I/O block, which we can use it to store and read data. But internally, inside the SSD, we have a lot of you know, fine-grained mechanisms to enable such things. So in SSD, actually, SSD controller is a complex system. Like you have essentially this component flash translation layer. We kind of discussed it also a little bit in the past, but just to now also I don't have time to go over it in detail. We're gonna see actually detail later. But the goal for flash, one of important goal of FTL or flash translation layer is to provide logical to physical address translation. So the addresses that come to the SSD from the host, they are in logical space, but internally you can map that logical address to different locations in your SSD. So there is this logical to physical address translation happening in FTL, which you know, provides that, which require to understand the location of your data stored in SSD. So this FTL actually has been executed on an SSD processor, which is a multi-core processor. It can be like 4-core, 8-core processor. And you do a lot of buffer management. And at the same time, also you have a flash controller, if you think, if you will. And these flash controller, they have ECC engines as well as signaling to such that you can communicate with the flash memory using those communications. So you can see that this SSD controller is actually very much a sophisticated system. And that's why actually people call storage as a storage subsystem, because actually you are building a system to operate on all these flash memories. And now you can actually also think about it a bit critically. Does it make sense to, you know, have such a complex controller or, you know, system and only do read and write? You know, you only read data from flash memory and write to flash memory. And the whole system that you're designing there, this SSD controller, is to serve for that. So that's why actually we have done a lot of work. Other people also work on it by doing computation inside the storage. And that's storage-centric computing, that you can benefit from the, you know, the heterogeneity and reach computation capability that you have inside the storage to do computation. Okay. So that's one example. So here, actually, in SSD controller, you do, complex error correction, where leveling, which I describe it, voltage optimization, when you want to do read operation. All these things are actually going to be much clearer when we, in our flash memory lectures. Garbage collection, page remapping, and so on and so forth. So there are a lot of tasks that this SSD controller is doing. And when you compare it with a DRAM controller, you can see that this system is something else. It's just a very intelligent. And essentially, many of the ideas that we were discussing in the DRAM latency lectures and data retention time, in order to implement them, you actually need to make DRAM controller much more intelligent in the line of SSD controller, essentially. Here is also another picture of that in another paper, which actually I suggest this paper some time ago also. I will suggest it again and again because it's a beautiful paper. But yeah, this shows the SSD controller that communicates with different flash chips. So essentially in this survey, and we described different errors, like there are many errors, and there are different mitigation techniques for these errors. Like for example, here we are showing that errors which causing because of the program array cycling. So when you are when you do a lot of program and arrays, like PA cycling, you are aging your flash cells, and that can cause some errors. Another error type would be when you are programming your chip. Another error type would be cell-to-cell interference, which kind of similar to interference that we have, for example, in RowHammer in a different way, but you can also think about it. Also, the data retention error type, which is similar to also the DRAM refresh error. DRAM retention time error. And also another error type, which is read disturb, which we also have this read disturbance error in the in DRAM, which RowHammer is one example of that. RowPress is another example. But in Flash also you can have read disturber error, which is a bit different from that, but you can also consider it. And there are different techniques, mitigation mechanisms for these error types. And many of these techniques or similar techniques actually have been implemented in state of the art nowadays. So it's not just the papers or some ideas that people show. Actually, state-of-the-art SSD, when you buy it from the market, the SSD controller is handling with all these error types, just to make sure that you can get your data properly. Otherwise, good luck, because flash memories are considered as very error-prone. When you read from DRAM, when you read, you might have some errors, but if you don't push the latency boundaries too much, you should be able to properly read without ECC. But flash memories, it's almost impossible that you get data without error. So you always need to have a lot of techniques to make sure that you can read from flash memory. Okay. Any question? I don't expect you to know all the details here. We're going to cover a lot later, but wanted to just give you some idea. Okay, so it's also more up-to-date version of that survey paper. You can also check it if you're interested. We're gonna see a lot more, how we can design or improve SSD. So for that, you also need tools. So this MQSIM is a state-of-the-art simulation framework that we have proposed for modern SSDs. And you can also do a lot of, at the control level, you should also, SSD controller need to also do a lot of prioritization. There are a lot of requests. And so among these requests, you need to decide what to basically prioritize. And of course, having high performance and fair, scheduling, request scheduling is very important. And this for Flynn is one of them, which we will cover actually in our SSD lectures later. And also other works related to, the data sanitization and in modern flash-based storage system. And improving basically reducing read latency, which again makes the storage controller more intelligent. Okay, and there are a lot more and in this line, and this work then is also related to improving the parallelism inside the storage. It's kind of similar to, if you think about it, it's similar to SALP paper, sub-array level parallelism, that essentially we try to break some of the the global dependence that we have. So we talk about decoder there, which is one of the the global dependence. So we added some latches, if you remember, to break that dependency. And also in the row buffer, when you want to connect the row buffer to the global I/O circuitry, we described those isolation transistors, some switches, just to switch between different row buffers, essentially. So in this work also, we discussed about the global channels that we have inside the storage, and those channels can become bottleneck because they are shared across many chips, and how we can avoid those conflicts by providing networks. So we devised a interconnect inside the storage, to break some of these dependency. We're going to see more later. Okay. I was discussing about this work just during the break. One of my colleagues asked a question. The initial version of this work, actually, we submitted to ISCA 2018. And in the end, the paper got accepted in ISCA 2023. But for this paper specifically, because I'm the co-first author, I can say that it's not only because of the review process. The work was not really that ready, so we improved the work a lot, and we have done a lot to make it, a top-notch paper. And in the end, this paper got accepted. So it's not another story of getting rejection and resubmission. So it's also about getting actually reasonable, good comments from the review process, and we have done a lot justice paper. We discuss it, improve it significantly. So again, a lot of resilience, but in another way. At least the process was fair to me. So I wouldn't accept the early version of this paper also. Okay. So we will have lecture on flash memory and SSDs, but if you're impatient, you can also watch this lecture from Professor Mutlu in 2020. And we also had some PNS courses it's a bachelor level course specified for modern SSDs. So this, for example, one version of it, which we had in 2023. We might have it also in future, but if you want to learn a lot of details about SSDs, you can actually also watch those courses. Okay, any question? Let me see. Okay, so as you know, we have different types of DRAM. Like DRAM has different types with different interfaces optimized for different purposes. So commodity is DDR, DDR2, 3, 4, 5. And we also have low power DRAM interface for mobile, like LPDDR1, LPDDR5, and so on and so forth. We also have high bandwidth memory for graphics, like GDDR. In the past, NVIDIA had this GDDR. And now they still have GDDR, but at the same time, we also use HBM, high bandwidth memory, for their devices. We also have some interfaces, low latency, like EDRAM, embedded DRAM, and also RL DRAM. So those are some specific DRAM technologies that they provide lower latency, but it's not really easy to, have access to them. They are very expensive. And 3D stacking with wide I/O, HMC, HBM, and so on and so forth. So, but the interesting point is that underlying microarchitecture is fundamentally the same. So you have this 1T, 1C, except actually some of them like EDRAM, which might be a bit different. But in general, DRAM set is one access transistor and one capacitor. So it's just the fact that you have different interfaces, how you can access and, communicate your data in and out. So a flexible memory controller can support various DRAM types, but that comes with a lot of complications. So that's why actually memory controllers are not capable of supporting various DRAM types, because for some of these actually interfaces, you need to replicate logics a lot, because you cannot. So there are a lot of specific for these interfaces that you need to obey, and they are not necessarily also the same. So meaning that they are not. Sometimes difference is not only about different latency that you need to obey. Sometimes you actually need to do different signaling. So because of that, you actually, if you want to support different DRAM types, that makes the memory controller super complicated, and in the end, quite large. So memory controllers are currently also one of the largest, the component in our DRAM in our processor die, which I'm going to show later. But if you want to support different technology, different interfaces, that would actually increase the capacity even more. So that's why it's very difficult to support all types and also upgrades, if you will. And so analog interface is different for different DRAM types. That's what I said essentially. So here's also the table from one of our paper from Remulator, which I also showed before. Like there are different DRAM types. You can also, if you want, you can learn more about these types from these references as well. This is also another picture which I've shown from another paper that we try to understand the effect of different DRAM types on the performance of different workloads, performance, energy, and power consumption. But essentially, if you want to learn about all these different types, you can check our paper and also Remulator, and also this extended version of Remulator. And this work related to DRAM types and workloads, which we already go over. But yeah, so DRAM controller here, for example, this chip from AMD, you can see this DRAM interface is actually consuming quite significant part in our system. And if you want to have several channels, you need to actually have several DRAM controllers, right? So for each channel, you're going to have one DRAM controller, and each DRAM controller would consume significant area of the chip. So that's why, in the end, if you consume a lot of area for that DRAM controller, then you don't have enough area to allocate to your cores, and to essentially to compute. So that's why there is a interesting. I mean, there's a trade-off how much you can make DRAM controller complicated. Also, if I want to give you some story, like originally DRAM controller was not actually part of the processor chip. I don't know, like 20 years ago or so, DRAM, we had this separate chip, which whenever you wanted to communicate with the DRAM, the processor needs to communicate with that DRAM with that separate chip, which is a controller, and that controller would communicate with the DRAM. So after that time, by basically advancement in the integration technology like VLSI, people realize that they have lots resources, so why not also having memory controller on the same die. I think first AMD actually has started doing that, and then after that also Intel has done it, and now actually you can see that DRAM controller is the part of the processor chip, and that was I would say good design decision in terms of performance, because if you have a separate chip, you need to do several, at least two signaling, one from one chip to another chip, and then that chip to the DRAM, and that intermediate communication would cause longer latency. But of course, it didn't work out well in terms of flexibility. So when you buy a processor chip, you're stuck with some DRAM type. So you cannot test different DRAM types. And that's why, for example, when we wanted to do that experiment, on seeing the effect of DRAM, different DRAM types on the workload performance and energy consumption, we had to do with the simulators, right? Because there is no way you can do it on real system. But when you buy a processor, you can only access some sort of DRAM types. If you want to support some other type, you need to add another processor. And when you run that experiment, your processor is different, so you cannot isolate the effect from the memory type. But yeah, now also people are trying to consider again that maybe we should move the controller actually outside the chip. If you know, in the line of CXL, which provides more, you can essentially you can extend the memory capacity much more, and you're much more flexible. So the processor needs to communicate with the CXL controller, and that controller can actually handles many of memories. That's good from the flexibility and the fact that you can actually add a lot of memory. People are claiming that CXL would not affect memory latency, but I wouldn't buy that much. It's a bit, it doesn't sound well, when you related to the physics, essentially when you have a separate chip and you're communicating to that separate chip and that chip to another. Well, if you have sometimes also people try to talk about latency in a full pipeline mode, So when you have several requests and the pipeline is full, then okay, you can actually, you don't see a lot latency, because the pipeline is full and every cycle or every, you're getting output. But if you look at one memory access latency, that would not really, I cannot buy that. For example, CXL would not cause longer latency. On average, maybe, you may not get longer latency, but that's also with some grain of salt. But on every single memory access, if you will, you will get longer latency. And single memory latency is also important. Single access memory latency is also important for some specific application. When you want to obey some timing, when you want to guarantee some latency, you cannot always work with the average latency or effective memory access latency that you're getting. Make sense? Okay. I'm going to show you a bit some more chips. This is also a chip from Apple that's, significant portion of the chip is allocated to memory controllers. This chip also, again, for AMD, which you have this global memory interconnect, which, consume a lot of space. And this chip from IBM, actually, IBM Power 10, yes, which has, significant space for memory controller. Actually, IBM has this, was more in the line of CXL. So because in their servers, they wanted to have this, increase the number of cores and also increase the amount of memory. So they wanted to be able to flexibly increase the memory capacity and also increase the number of cores. So they couldn't essentially afford changing again and again the DRAM, the CPU structure when they wanted to add more memory capacity to it. So that's why they come up with this a little bit different design for memory controllers, which it allows you actually to expand memory capacity more easily, which is in the line of CXL, actually, if you will. So just some high-level information, but if you're interested, you can check more. So DRAM controller has several functions. So one function is to ensure correct operation of DRAM, meaning that we need to do refreshes, like DRAM controller needs to do refreshes, and we need to obey the timings. And DRAM controller needs to service DRAM requests while obeying timing constraints of DRAM chips. So there are also some constraints of DRAM chips, like resource conflicts, like bank, bus, channel. So you cannot. Also, you also nowadays you have a bank group, which adds another constraint. So there are these resources, like general global resources, that you have conflicts on them. And you need to be careful that DRAM controller, for example, cannot issue 2 requests that they are going on the same bus, right? It's going to be bad. And also, you have this minimum write to read delays, which is kind of unfortunate. But in order to reduce the cost, we have both basically bi-directional channel, from the host, from the processor to the memory. So you are using the same channel to write and also to read. So that channel is used in both ways. So that's why you can, when you are writing to the DRAM, you cannot immediately read. So you need to wait a little bit to set the direction of that channel to, to read and then read. And when you're reading, you cannot immediately go to the write mode. So essentially, you need to wait. And that's just to make sure that you are not burning that, that bus, because that can cause a short circuit. If you do it immediately, you're gonna cause short circuit in that channel, and that can burn either processor or the memory or both. I've done it actually in the past. Not with, not with like modern processor, because modern processors, a bit different. But with some ICs, I was doing that, and there was a bus that we had to control it from both sides, and I didn't obey some timing, and I burned some ICs in our labs in the past. But it was fun, I learned from experience. Okay. There are also some other functions like buffer and schedule requests for high performance and quality of service. Like there are a lot of requests going through the memory controller from one core, from multiple cores, from different threads. So you need to buffer them, because usually the rate that you're getting requests is actually much higher from the rate that you're servicing requests, because memory DRAM is slower, right? So you need to buffer them, and then you need to make a lot of decisions what to prioritize for high performance, for quality of service, for fairness. So there are a lot of operations like reordering that you might need to do, considering the row buffer, in your chip, DRAM chip, bank, rank, bus management, and so on and so forth. And also the memory controller needs to manage power consumption and thermals in DRAM. Like do this turn on off DRAM chips, manage power modes. So like, for example, at some point, memory controller realized that you are not touching some part of the DRAM. So there is some power mode, which is named as self-refresh mode. So the memory controller puts that DRAM part of the DRAM to self-refresh mode. Is that I'm not accessing it, just internally do some refresh to make sure that you don't, destroy the data. But of course, if you want to access that DRAM region, you need to come out of that mode in order to access. Okay, so yeah, let me see. Yeah, this picture, I can also quickly go over it, but a bit not a lot of detail. But essentially, in DRAM memory controller, you have you can have CPUs, I/O, and all of them are generate request streams, and they come to this memory controller. And in memory controller, you have some arbiter in order to prioritize these requests, and then you can put basically these requests in their different bank level queues. Like you have different banks, and then you can have queue for each bank, and then you essentially insert these requests to these different queues. But then later on, when you want to also access DRAM, you're operating on some shared channel. So there should be also some arbitration across these banks, across these queues, to decide, okay, who to take the bus cycle. And there is also an important part of the DRAM controller, which is signaling interface, which does a lot of digital to analog and analog to digital, which one of the hardest part of the DRAM controller, in order to obey all these timings with high frequency that we have. So it's very hard to design. There's also another view of modern DRAM controller, which you get requests from last level cache, for example, here L2. And then you have different buffers considering your bank number. And so for all these requests that they are storing in that, each of this buffer, like for each of these bank, you have some scheduler to prioritize across these requests. But however, across all these scheduling, you also need to do some global scheduling. So you have some local scheduling across the scheduled requests that they are available in the bank queue. But you also need to do some global scheduling, because in the end, you have some shared global channel, which all of them, they cannot access it at the same time. So you do this global scheduler across all these local scheduler to in the end schedule one request to the DRAM chip. Make sense? So yeah, this part is I will stop here. So next week we will continue with DRAM scheduling policies, and we're gonna see more about, not next week actually, tomorrow. So we're gonna see a lot more about functionalities of DRAM controllers and how we can improve it. Is there any burning question? Is that really burning? So nowadays, actually, we have on-die ECC on DRAM chip. So DRAM controller, I think, does not do. I mean, you can also do that. You can add more ECC support at the DRAM controller, but I'm not sure. I don't know about that. Okay, so let's part. See you all tomorrow. Thank you.